So hopefully you have done the review on complex numbers, and now we are going to start how we are going to use complex numbers in AC and stuff, okay, in electrical system. But before that, I need to tell you something, that here we actually use J, small letter J. So this is my small letter J uh, as root over -1 instead of I, because we actually use I for current a lot here. So that's why we are going to use square root of -1 and denote this by J. So engineers always use J for complex numbers in calculations, and you can actually see that in Python. If you write 3 plus 2i, 2 times I, it will actually not work. But if you write 2 times j, it will actually work. And 3, I guess you can write 3 plus 2j, it should also work. So Python has built-in complex numbers, but they uses j, because engineers use j for complex numbers usually. That's why we are using that. And one more thing, the fact that e to the power r times e to the power I theta, we actually don't write these things this much. We actually use a shorthand for that, r theta, and we use degrees for the thetas. Okay, so keep these things two things in mind. Okay, but it really actually doesn't matter. For example, if I say 5 angle 30 degree divided by let's say 2 angle 10 degree, it actually equals to 5 divided by 2, 2.5, then 30 degree minus 10 degree. Remember, if it's division, you just subtract the angles. So you have 2.5 angle 20 degrees. And if you have, if you want to multiply two numbers, all you got to do is just multiply the radiuses. 5 times 2, 10, times 30 degree plus 10 degree. That is, in total you have 40 degree. So this is how we multiply two numbers. Okay, and for addition, well, this is like the vice versa of rectangular or Cartesian system. So this is actually harder to add two numbers in polar format, but we always have calculators for that, so don't worry. You can do all of these calculations in complex modes. Okay, so now the question is, okay, we have done complex number reviews, but how do we actually use this in actual AC circuit analysis? So before that, I actually want to show you an example. So why use complex number at all? Okay, so there is an important fact regarding complex number, that it can actually add rotation. Okay, so for example, if you have any complex number 3 plus 2i, okay, and if you multiply that by, so if you multiply 3 plus 2i by, let's say, e to the power I theta, that is, I'm going to write it like our in our electrical system, so 1 angle 30 degree, that would mean, well, the radius remains same because you are just multiplying by 1. So whatever the radius was, this radius remains the same. Okay, so the radius remains the same, but it introduces 30 degrees, so it adds 30 degree to the already existing, let's say, theta degrees. Okay, so it introduces some rotation into the system. So this is what complex numbers are really useful for. Okay, so you can describe rotations in the systems. Not only that, you can also actually describe cosines and sines, right? So we have seen in the past, right, that in general this was like r cos theta plus I r sine theta. So you can imagine if we keep changing the theta, okay, if we keep changing the theta, our r cos theta will change, and this will obviously change in a cosine pattern, right? So this is why we can actually represent cosine in terms of, we can just write, okay, we have a complex number 3 plus 2i, but we will most likely use the polar format, and we will say that, okay, the real part of a complex number is basically a value multiplied by cosine, right? So this is how we denote our cosines, and this is how we work with it. So here, yeah, so this is very useful. And for example, one of the applications I can show you right now, that let's say the cube roots of 1, okay, so you have seen this problem in HSC. Maybe a refresher would be very good here. So what's the cube root of 1? Well, cube root of 1 is 1, obviously, but there are two other roots. We don't usually talk about them because they are complex, but there is two other roots. So one of them is the 1 plus root 3 times I divided by 2, as far as I remember. I don't actually clearly remember. And 1 minus root 3i by 2 or something like that. Okay, so the conjugate of that. Okay, I can't actually remember that number. Is it like 1 over root 2 divided by root 3 or something like that? I don't actually remember. Okay, so I don't know. So let's figure it out. Is there any other way to represent this thing? Okay, I don't actually remember how to write that, and at least I am pretending not to. And you can also think, okay, yeah, that was hard. Let's see if the polar format makes any sense. Okay, so if you can remember that actually one of them was called omega and the other was called omega squared or something like that, right? Because if you multiply that 2 times, you would actually get the other. Okay, and actually I can write very easily what omega is. Okay, maybe, okay, usually in textbook maybe this was written as omega and this was written as omega squared. If we actually plot the 3 roots, the first root is here 1, the second root is here somewhere around there, and the third root is somewhere around there. Okay, so I think the value should be -1 plus root 3 and -1 minus root 3 or something like that. Okay, so this must be kind of like that, and like I said, I actually don't know. But in polar format, this is very easy to write. Okay, instead of writing it like this, we can actually easily write, so maybe this we can actually write this as 1 angle 120 degree. So let me write it again, 1 angle 120 degree, and we can write the other as 1 angle 240 degree or minus 120 degree, whatever you prefer. Okay, you can go clockwise 240 degree, or you can go clockwise clockwise 120 degree. I meant to say anti-clockwise in the first case. So you can go anti-clockwise 240 degree, or you can go clockwise in the clockwise direction in 120 degree. Okay, so this is your 1 minus 120 degree, and this is your 120 degree. The radius is 1, so this is 120 degree. Okay, and this is also 120 degree, and this is also 120 degree, and hopefully you can see y root cube cube root might be equal to 1 times 120 degree. This is because if you cube this, so okay, if you cube this becomes a 1, and if you cube the both sides, well, you get 1 cubed, that is okay. So let me write it out for the first time. Okay, so 1 times 1 times 1, which is also just 1. 120 times 120 times 120, which is 360 degree. And we already know that 360 degree is just 0 degree, right? So this is actually our 1, because 1 is 0. So you can actually write any real number as 10 degree, just positive numbers like that. And if you are working with negative numbers like -2, you can write that as 2 angle 180 degree. Okay, so this is how we write just a positive radius and an angle. Okay, so this is why yes, so cube root of 1 is just 1. Cube root of 1 is 120 degree. This is because if you cube that 3 times, you will get 1, right? And you can show the same for 1 angle minus 120 degree. If you cube that 3 times, you will have 1 minus 360 degree, which is also just 10 degree, or just simply 1, right? So this is how we can actually very simply see what's the result, right? And actually we can generalize this to any n root. Okay, so now if I ask you what's the 5th roots of 1, so there will be 5 roots, and they are very simple. So the first one will be 1, because, well, obviously root over 5 of 1 is equals to 1. But this 360 degree is divided into 5 spaces, right? And so if you divide that, you would get what, 72 degrees, right? And so this will be something like this, I think. Yeah, something like a star, right? So this is 1, and this angle is 72 degrees. So if you go 72 degrees anti-clockwise, you will reach 172 degree, and that's the root of 1, because 172 degree times to the power 5 is actually 1 to the power 5 times 72 degree times 5. So this is times, because, well, this was actually in powers. So 360 degree, you have just 1, and then you go another 72 degree, you have another root. So this is 72 times 72 plus 72, right? So this is 144 degree, right? Yes. Then you can go another 72 degrees. You will have 216 degrees, and the last one is actually well, okay, I think instead of writing like this, I would rather prefer like minus 72 degree. That's much easier. I don't have to do any computation. Okay, so this is our results. So we can write him like this. And so as you can see that we just generalized this thing very simply. If I ask you the same question, okay, what are the 5th roots of 1 in Cartesian, that would be much tough for you to solve, right? You have to solve x to the power 5 equals to 1. What does it, x to the power 5 minus 1, factorize them, etc., etc. Okay, so you have to do a lot of calculations for that. You don't need any of that. You can just simply do this. So this is why polar formats and complex numbers are very, very important. And we are going to introduce a few things related to alternating currents that will use complex numbers. So we are finally ready to use complex numbers. Before ending the lectures, these things are also called phasors. Okay, so these are also called phasor. This comes from physics background, and I don't want to go to details, but in electrical systems we will call them phasors a lot. Phasors. Okay, we'll call them phasors and use that term to describe basically complex numbers written in polar formats like this. Okay, so thank you. Let's meet on the next lecture.